Hi, my name is Nathan Glover, and today I'm going to continue with my next video for my project HandMap. I'd like to start by discussing what we got up to last time. We just finished discussing HSV versus RGB color detection methods, and we'd broken down and gotten an angular mapping process finished, and we explained broadly how it worked. Then, I demonstrated the angular mapping process in a short video. Before I get started, I'd like to quickly go over my original problem statement and review it. My plan is to design a system that can accurately measure and map angles, distances, and key points on a hand of various shapes and sizes. The system should be modular enough that it could be dropped into pretty much any other medical area, or any area for that matter, without too many changes being made to the core functionality of the software. It should use standard cameras, typically found in most smartphones, and be non-invasive. All the work I've done up to this point has been using desktop versions of OpenCV, mainly on Java and Python and some C++ programming languages. I wanted to briefly look at the complexities behind producing a mobile application on the OpenCV platform, and decided that I'd use an existing Unity 3D package that handles OpenCV to develop an iOS or an Android application with OpenCV. Unity 3D typically uses C# or JavaScript, but the examples I was looking at use C#, which is fairly similar to Java. I looked at an example of multi-object tracking within Unity 3D based on the color values of the objects. It performed really quickly and in real time. The code was laid out in a very readable way, and I decided I'd explore the original design implementation by the author to see if I could get any ideas and things that I could bring back to my project. Exploring the class structure, I found that the software was designed to be very modular. Each object that was detected was stored in a custom data type that housed the definition of the object's color, the position, and a reference to the image frame. The colors were also stored in their own custom class called color object. Each color object had a defined HSV min and max value and would set a color or an RGB color based on those thresholds. The benefits of using a class structure like the one outlined in the example means the implementation is very portable and modular. It's scalable and lets you change a lot of the key variables within the code easily by using their preset global variables. I decided that I would take a lot of the ideas I'd learned from this example back to my project design. My next goal was to come up with a method of calculating real distances between points. My concept was to use the sensor as my reference scale, and to draw and calculate lines out from key points to the hand. If you pair this with the angle mapping design, we would start to have a lot of usable data for our medical splints. The implementation for this design was based on a fantastic example by Adrian Rosebrock. We supply the program with a static width of the object we want to use as the reference scale. We ensure that the object is the leftmost object in the image, and we find the largest contour in the image, adding a bounding box and its measurements based on the reference scale. You can see an example of this to the right of this slide, but we run into a very obvious problem. The hand is considered one large contour in its current state. We require some modification to limit the size of each contour, but for now we won't worry about that, as we only really care about the distances to clear convex and concave regions on the hand, i.e. the points on the fingertips and in between the fingers. As a very simple workaround, I edited my reference image to test a simple example. I edited in a picture of the blue sensor with a reference width of 0.995 inches that I could use as my scale reference point. The results speak for themselves in the images shown in the slide, as you can see that the lengths between the blue sensor and various points in the hand are accurately displayed. This is where we run into our next problem, which is depth of field. One of the biggest drawbacks of using this method is that our system is limited to a 90-degree plane, i.e. taking the photo from directly above the hand. If we did capture an image from the front, as shown in the image, we would get an inaccurate measurement saying the index finger and middle finger were very different lengths, when in reality they are pretty similar in size. I spoke to my supervisor about this problem, and we came up with a plan for me to follow for the next video, and that is, I'm going to place a camera 90 degrees above the hand's plane and measure the distance of the two objects. Next, I'll move the camera 5 to 10 degrees, accurately measuring this degree value, and see what kind of differences in offsets I get. This will allow me to determine the angle ranges that will produce the best and most usable data. I also thought now I should mention that I have begun writing my thesis and have decided to format it using LaTeX, or LaTeX. If there are any other students that require a simple template and want to start learning LaTeX, then please ask me and I can provide that for you. This concludes my video for part 4. If you have any questions, feel free to email me on nathan@glovers.id.au or check out my project blog. I also have a fairly active Git repository for the hand map progress on github.com/handmap, and feel free to have a look there or make changes and push changes if you'd like to help or find something wrong with my code. Anyway, thanks again, and I'll see you next time.